Okay, hi. So in this video we will continue our study of Fourier series. We will see Fourier series in action. So let us begin with a periodic signal x of t which has a period t. So since it is periodic, x of t plus t plus capital T is x of t, and the fundamental frequency of the signal is defined as omega naught, which is equal to 2 pi by t, right? Because x of t is periodic, it covers 2 pi radians in t seconds, capital T seconds. So omega is radians per sample, so it is 2 pi by t radians per sample, that is omega naught. So we have also seen complex exponential signals. X of t here is e raised to j omega naught t. So this signal we saw earlier that it is periodic, and it has in this case the fundamental frequency is omega naught, and the fundamental period is t is equal to 2 pi by omega naught. So you have to first decide the period, and from the period you get the frequency, or vice versa. First you decide the frequency, and from the frequency you get the period. Anyway, so we also saw harmonically related complex exponentials, which is a set of family of signals, which is a set of signals here. So we denoted this as phi of k, phi k of t, where each signal in this set is obtained by varying the value of k. So each signal is e raised to j k omega naught t, right, where k takes on value 0 plus or minus 1 plus or minus 2. So essentially each signal in this set has a frequency which is a multiple of e raised to j omega naught t, which is the fundamental or the first harmonic component. Okay, so now suppose we sum up, suppose we take a linear combination of a set of harmonically related complex exponentials. So essentially what we have done is ak, some coefficient here, ak multiplied by e raised to j k omega naught t, and you vary this over, you take this linear combination by varying the value of k, okay, where k is taking on the value 0, plus or minus 1, plus or minus 2, and so on. So this is essentially the Fourier series representation of x of t. So essentially in Fourier series representation, we are representing a signal, a periodic signal x of t, in terms of linear combinations of harmonically related complex exponentials. Okay, now because of the property of harmonically related complex exponentials, all of them are periodic with the period capital T, right? The x of t is also periodic. The signal which results from the linear combination is also periodic with the same period t. So this is the essence of the Fourier series. So let's see an example. This is example 3.2 from the book, because this is illustrative of the idea. So here we have taken a finite linear combination. X of t is equal to k goes from minus 3 to 3 ak e raised to j k 2 pi t. Okay, so here our capital T here is 1. Okay, so the period of the signal is 1. So we are also given the coefficients a0, a1, a minus 1, all the coefficients are given to us, and hence since we write x of t as this, so we will just expand this, substitute each of the values here, and we expand this out, and essentially we will see what we get. Okay, so x of t, I just write it in terms of these coefficients which are given to us, and we get, so if you combine these two terms, okay, this is k equal to 1 and k equal to minus 1. This is k equal to 2 and k equal to minus 2. This is k equal to 3 and k equal to minus 3, and these are the coefficients. Okay, so this is e raised to j 2 pi 3t, e raised to j 2 pi 2t, e raised to j 2 pi t. Okay, so these are the three harmonic components which make up x of t. and of course the when k is equal to 0 you have a constant signal. So if you see this, you can just combine these two by using Euler relationship, and this is nothing but cos 2 pi t, this is nothing but cos 4 pi t, and this is nothing but cos 6 pi t. So I combine, so if I illustrate it pictorially, I can see each of these components. The constant signal 1 is like a DC signal. It's a constant. It doesn't change. This is time axis. It doesn't change. This is constant. This is nothing but cos 2 pi t, that is, which is nothing but a sinusoid with period 1. This is cos 4 pi t. This is again a sinusoid. This is also a sinusoid with cos 6 pi t. So essentially now on this column it shows how at each step how the original signal x of t is being formed. So this plus this will give you this plus this will give you this plus this plus this plus this will give you this. So essentially this is my x of t. Okay, so in Fourier analysis, we actually, like I said before, we actually do the reverse. We are the most of the time the objective which we will be doing is we will be given x of t, we will be given this. Our interest is to find out the constituent components of the harmonically related complex exponentials which make up x of t. Okay, so this is actually what they have done here. This is the Fourier synthesis. Okay, here how do you build x of t given these harmonically related complex exponentials? So one thing also to note here is that each of these AKs, although we are writing them in terms of complex exponentials, we are writing the x of t in terms of complex exponentials. Finally, the final x of t which we get is a real signal. Okay. So the question remains, given x of t, how do you perform Fourier analysis? That, in other words, how do you compute the AK? That is the question, because here in this case AKs were given to us. The AKs were given to us, so we were just building x of t using the AKs. Now how do you do the reverse? Right? Given the x of t, how do you compute the AKs? So there is a derivation in the book. You can see it in section 3.3.2. It is not very difficult, but this is the essence of that derivation. This is the final output. This is what we have seen before. X of t, we are writing x of t as a linear combination of complex exponentials. This 2 pi by t is same as your omega naught. Okay. And the AKs, if you are given the x of t and if you want to find out the AKs can be computed by using this expression, which is 1 over t divided by integrate this expression over one period t. Okay, so here in all cases we are assuming that x of t is periodic with a period t. So it is just found by x of t e raised to minus j k 2 pi by t dt. So you can see that the expressions are very similar. The only difference is that to get the AKs, we take the complex conjugate of this. Okay, so the reason for this we will touch upon it later in some in a future lecture. So these two equations are the crux of the Fourier series. This, which we saw earlier, is the synthesis equation. That is, how do the different complex exponential components which are harmonically related build up your x of t? That is the synthesis part. So that is that is the analysis part. Sorry, how does let me repeat. So combining the various harmonically related complex exponentials with their respective scaling factors, giving us the x of t, is the synthesis equation, and the finding of the respective coefficients AK is the analysis equation. That is done by this expression. Okay, so these two form the crux of the Fourier series. Please note the similarity and please remember how they are distinct. Let's take a couple of examples. This is again all from the textbook. Example 3.3. How do you perform Fourier analysis on x of t, where x of t is sin omega naught t? We know this is a periodic signal, sin omega naught t. So you can just use the Euler expression. You don't have to explicitly compute the AKs, because you can directly write down the AKs by observation. So we write you expand the sine omega naught t using the Euler formula, Euler relationship, and from this, so these form our A1. These form our the first harmonic component, because basically sinusoid has only one harmonic component. There is only a single harmonic which makes up a sine omega naught t. So essentially there is only one harmonic here, and these are the AKs. Okay, so here is only A1. This is A1 and this is AF minus 1. Essentially, so in general, although our signal is sine omega naught t is a real signal, the Fourier transform coefficient of the Fourier series coefficients could be in general complex. The other AK coefficients, because it is an infinite combination, the other AK coefficients are 0. Another example from the book, this x of t is written like this: 1 plus sine omega naught t plus 2 cos omega naught t plus cos 2 omega naught t plus pi by 4. So this is a cosine signal with a small phase shift of pi by 4 radians. Again, whenever you have sinusoids, you can use the Euler relationship and expand each of them in terms of complex exponentials. So this, if you just expand each of these terms, you will be able to get the respective AKs. So this is A1 and this is A minus 1, this is A2 and A minus 2. We have only expanded out each sinusoid as a complex exponential by using the Euler relationship. So now we get the A1s, A2s, and the A0s, which are the three components which make up this. We have A0, A1 and A minus 1, A2 and A minus 2, which are the coefficients of the various harmonics which make up this xt. And so since these are complex numbers, each of these AKs here are complex numbers, you cannot plot them in a single plot. You need to plot them separately. You need to plot the magnitude and the phase, or the magnitude and the angle, separately. So this is the magnitude part, and this is the angle part. This is the magnitude of AK, and this is the angle of AK. So for every k, so this is my k axis. This is my k axis. So it's a discrete axis, because the Fourier series coefficients are discrete. It's a series. It's not a continuous function. It's a series, right? The coefficients go from 0, 1, 2, 3, minus 1, minus 2, minus 3, so on. So for every k, find out the magnitude. So here in this case, there is only 1, 2 and 0. So 0, it is basically, this will have a magnitude of 1. This is the magnitude of 1 plus 1 by 2j, magnitude of that. The magnitude at minus 1 also, you have the magnitude of 1 minus 1 by 2j. Take the magnitude of that, then you get plotted from minus 1, and that exists for minus 2 and 2. All the other coefficients are 0. And similarly, this is the angle corresponding to each of these coefficients. Okay. So the coefficients are only from 0 to 2 in both directions. So that is why you have the plots from 0 to 2 in both directions. Another interesting example from the textbook is example 3.5. So now this time we have a signal which looks like this, which is a periodic square wave. Okay. So this square wave is periodic with a period of t. Okay, but this is a symmetric square wave, that is, in terms of how it is with respect to its location, with respect to the origin, with respect to the y-axis, it is symmetric. Okay, so the square wave has a period t, and then it keeps repeating after every time period of t. So you can see that the part of the square wave, so the part of the square wave is from 0 to t1. I have a interval 0 to t1 where the x of t takes a value of 1. So this value is 1 from 0 to t1. The remaining part till t by 2, it is 0. Okay. So this is, we have shown it as absolute value of t, so it extends to both sides. Fine. And this repeats. This is how the square wave is built. So this is t and this is t1. Okay. So t1 is the so you can say t1 is the within a period, half of t1 is where the signal is going to be 1, because this half, this is t1. So there is a t1 here and also there is a t1 here on the other side. Okay. So this is the signal given to us, which is basically a symmetric square wave. Now, how do you compute? How do you come up? How do you do Fourier series analysis on it? It is a periodic signal, so you can do Fourier series analysis. So how do you come up with the AKs which make up this particular signal? So for this, you have to use the expression, the analysis equation which we saw here, which gives you the expression for AK. So let's first do it for A0, which you substitute in that formula for k equal to 0. So you get 1 by t over any period. So we have taken the period from 0 to t, but actually since most of it is since it is this, the signal is 1 is 0 all the other places except between minus t1 to plus t1. So we can calculate it as minus t1 to t1 dt, so this is 1, and you get 2 t1 by t. Now for when k is not equal to 0, so that is the first coefficient, a0. Now to compute the Fourier series coefficients for the other values of k which are not equal to 0, again you substitute in the expression 1 by t, again we do it over minus t1 to t1, and now it is e raised to minus j k omega naught t, because this is the expression dt. Okay. So if you solve this formulation integration, if you solve, you will get 2 sine k omega naught t1 by k omega naught t. This expression is what you will get, and k is not equal to 0. So this is the values of ak which you get. So in this case, note that the Fourier series coefficients are actually real. Okay, the Fourier series coefficients here are real. This is a real number, it is not a complex number. Whereas in this case, this was for this particular x of t, we saw that the Fourier series coefficients were complex, but in this case it happened to be real. Okay. So here is the plot of these real coefficients, because it is real, because because it is real, there is no phase plot, there is only one plot which directly gives you the coefficient values. So this figure is again from the textbook. So they have shown it for various cases as the difference between t1 and t is varying. Okay. So when t is equal to 4 t1, let's say, so that is it is each t1 is 1/4 the width of the total period t. Okay. So this is 4t1. You get a spectrum like this. This is the Fourier series coefficients, plot of the Fourier series coefficients. So you can see that they are slowly decaying. They are slowly decaying. It is not really 0. Okay. So in the earlier case, we had only a finite number of Fourier series coefficients. Here we had only finite, but here we have more than a finite number. So this is for 8 t1 and this is for 16 t1, when the ratio between t1 and t is 16 times. Okay. So essentially you can see that as the proportion of the non-zero part of the square wave, or essentially as the square wave gets narrower in width, you can see that the spectrum becomes broader. Okay, and as it becomes broader, the spectrum becomes sharper. Okay, so this is a kind of relationship which you will see frequently in Fourier analysis. If you become smaller in time domain, so here this is becoming wide in the time domain, right? Because the time domain representation of x of t here, and this is the frequency domain representation, because we are seeing the Fourier series spectrum. So as you can see that it becomes broader in time, it becomes narrower in frequency. Similarly, if it becomes narrower in time, it becomes broader in frequency. So this kind of dual relationship we will keep seeing in the Fourier series. Fine. So you can please go through this from the textbook and please work out the examples.